Welcome to the Explainer. Today, we're taking a virtual gallery tour right into the futuristic workshop of human-machine collaboration. We're going to explore how artificial intelligence is fundamentally changing the way we create, preserve, and really understand the physical world around us. It's completely transforming from a simple digital novelty into a highly specialized, absolutely crucial instrument for the modern craftsperson. Okay, let's dive into this. Here is our roadmap for today. We'll start with the artisan's new tool, move on to correcting the cosmic blur, explore the math of music, reviving relics and rides, conserving historical crafts, and finally look at the future of collaboration. Section 1. The artisan's new tool, precision over replacement. We really need to kick things off by busting a major myth. AI isn't just some blunt hammer coming to replace human art and expression. Actually, in the hands of modern artisans, it's a high-tech scalpel. You see, general-purpose AI, the stuff trained on massive, random sets of natural landscapes and text, tends to hallucinate features. It offers a very blunt type of generation. But domain-specific AI, well, that's where the real magic happens. These models are trained on highly specific linear data. They are strictly physics-informed and designed to resolve incredibly complex mathematical problems without just making things up. So for the rest of this explainer, we're focusing entirely on this specialized, domain-specific AI. Moving on to Section 2, correcting the cosmic blur, AI in astrophotography. Let's take our gallery tour up into the stars. Imagine a telescope sitting at the bottom of our ocean of air, fighting all that turbulence just to capture faint light from light years away. That struggle creates the point spread function, or PSF, which is essentially the specific, messy blur caused by our atmosphere. It's kind of like looking through a wavy glass window. Now, if you throw a general AI at an astronomical image, it completely ruins it. It interprets diffuse gas clouds as compression artifacts and just hallucinates features. But specialized neural deconvolution dynamically evaluates the specific, local blur. To really wrap our heads around this, we have to look at the math that anchors optical blur directly to physical reality. It's wild to think about, but the image we actually observe, represented here by the letter I, is really just the true star signal, O, tangled up in a messy knot with H, which is that blur we just talked about, plus the camera noise, N. Domain-specific AI is uniquely capable of untangling this exact knot to recover the true original signal. And that brings us to specialized neural architectures like BlurXTerminator. This is a real game changer. It literally decouples point source stars from delicate background nebular structures. It corrects optical aberrations like coma and tracking drift, and it even reduces star diameters without creating those ugly dark halos. Crucially, it operates very early on linear, unstretched sensory data, acting as the absolute perfect digital assistant to the modern astronomer. It means we aren't just making pretty space pictures, we're recovering the actual physical truth of the cosmos. Section 3. The Math of Music, Computational Lutherie. We're bringing our tour all the way back down from the vastness of space and stepping into the dusty, tactile woodworking shop of the modern luthier, the craftspeople who build stringed instruments. Historically, making a guitar relied entirely on an artisan's intuition, right? Manually evaluating wood stiffness and tap tones. But today, it relies on the number 4. Computational Lutherie models an acoustic guitar using 4 degrees of freedom. It essentially breaks the instrument down into 4 main vibrating parts that act as one highly interconnected system. When AI maps all this out, we get 3 primary resonant modes. First up is the air mode. Think of that low hum when you blow over an empty glass bottle. That's driven by the guitar's internal body volume. Then we have the top monopole, which is the fundamental soundboard resonance driving the mid-frequencies. And finally, the back monopole, which interacts with the top plate through the internal air spring. We are quite literally grounding incredibly complex differential equations into the breath and vibration of the guitar. Now, behind those beautiful, warm vibrations is the equation for flexural rigidity, which dictates the structural resistance to string tension. Running full 3D simulations of this takes massive computing power, but machine learning surrogate models can now use these mathematical relationships to predict timbral variations in real time. It is absolutely incredible. We can digitally hear exactly how a carbon fiber brace will change the instrument's soul before a single piece of wood is ever cut. Section 4. Reviving relics and rides, automotive metrology and digital twins. Let's shift our energy from delicate acoustics to the metallic, greasy, beautiful world of classic car restoration, where missing original blueprints are a massive headache. This closed-loop workflow is the ultimate solution. We start with optical metrology, using non-contact 3D scanners to capture complex chassis assemblies safely. Then, real-time AI filtering strips out all the reflections from metallic paint and background noise. From there, we move to feature-based parametric CAD reconstruction. We verify the surface deviation, and finally, go straight to direct CNC machining or 3D printing of the exact replacement part. Step 4 in that amazing process relies entirely on the formula for surface deviation. This math guarantees a precise fit by calculating the exact distance between the physical point cloud we scanned and the new digital parametric CAD surface. The software visually maps this as a color-graded error gradient, ensuring absolute physical fidelity for critical components. And this matters immensely, because let's be real, in a classic engine, if your cylinder head is off by even a fraction of a millimeter, the thing simply doesn't run. Section 5. Conserving historical crafts, reconstructing textiles and manuscripts. I'm going to gently guide you out of the machine shop now and into a quiet virtual museum. Standard optical character recognition, or OCR, completely chokes on degraded historical manuscripts. Stains and ink bleed just trip it up. But advanced handwritten text recognition uses adaptive binarization. It essentially teaches the computer to separate the original ink from centuries of decay. This massive technological leap allows archivists to save and translate severely decaying historical texts that traditional scanning software just plain cannot read. But hey, it's not just about preserving text either. Deep neural networks can actually infill missing ornamental motifs on degraded historical tapestries based on their surviving symmetries. We also have dynamic cloth engines calculating flexural rigidity and shear resistance, letting us build full 3D meshes for augmented reality virtual digital wardrobes. Just imagine virtually trying on an 18th century gown right in your living room and watching the ancient fabric move naturally, all without ever touching or destroying the fragile original artifact. Section 6. The Future of Collaboration. Synthesis across domains. We've walked through some vastly different rooms on our gallery tour today, but look at how deep into the human experience this shared technology really goes. Over in neuroacoustics, AI is generating real-time soundscapes based on your body's daily rhythms, using auditory beats to help your brain lock into a state of deep flow. Expressive neural vocal synthesis models are evaluating narrative emotional arcs, and real-time pose estimation is tracking dancers on virtual concert stages. It is literally mapping our biology to art. So, what's the crucial takeaway here? It's the common thread between all these incredible fields. Whether we are correcting optical blur in deep space using neural deconvolution, modeling acoustic stiffness in a guitar, reverse engineering classic car parts using point clouds, or building virtual wardrobes with photogrammetry, they all share a unified computational architecture. They all take unstructured, messy, real-world physics, apply a highly specialized AI paradigm, and output a refined, physically accurate result. Across all these domains, because the AI is strictly informed by actual physics, the outputs genuinely conform to real-world mechanics. No hallucinations here, just a profound democratization of industrial-grade tools for everyday creators. We are building unified digital twins that safely preserve our fragile physical heritage. Ultimately, AI is tightening the feedback loop between digital design and physical execution. It handles the dizzying math so that human artisans can focus purely on the soul of their craft. And that leaves us with one incredibly exciting, provocative thought to end on. As domain-specific AI masters the complex mathematics of the physical world, what long-forgotten creative projects will you finally bring to life? The tools are no longer science fiction. They're here, right now, ready for your own human-machine collaboration. Thanks so much for joining me on this explainer, and I absolutely cannot wait to see what you create.